Okay, so let us come to this this topic, capacitors and inductor. We have just started with that, right? So now let us consider what happens as current flows through a capacitor, right? Suppose the current flows downwards as shown in this figure, right? So it is this is shown the direction of the current, that current flows, and electron it is given that flowing upward actually, and in between this is your dielectric material, and these two, this one and this one, these two are conducting plates. So as we have taken the direction of the current moving upward, generally in any metals, right, that your what you call that whenever current flows means it is basically your what you call that moving of your electrons, right, just in that your what you call, if current direction we take upwards, electron moves just in opposite direction. So electron flow will be upward. So this is that electron flow. So because of that electrons actually this is your upper plate and this is that bottom plate, say. So here that it your what you call electrons will be here on the bottom plate. This means that negative charge actually will be accumulated or will be collected in this your what you call bottom plate. That is why it is shown minus minus minus, then your negative charge. So because of this there will be an electric field will be created in this dielectric material, and electric field will be created, and because of that you are in between these two plates, and this will force the electron to leave the upper plate at the same rate the way it was accumulated at your the bottom plate, right. In that way, then and the current and direction of the current will be downwards, and if voltage your what you call that applied across your these two plates. So and if charge gets accumulated in other way, or voltage if you apply across these your two plates, naturally your what you call that your charge will your accumulate either at the bottom plate or at the top plate. But remember that total charge will be either at the bottom plate, this will be plus q, or here it will be minus q, but total will be 0, upper plate or lower plate, total will be 0, right. But question is that when you say the total charge accumulated on this of the capacitor means it is either upper plate or at the lower plate, right. So let me clear it. So all this explanation is, this is the diagram, and all this explanation is here. Whatever I said, that in most of the metals, right, the current consists of electrons moving and conventional current flowing downwards, you are right, represent that electrons actually moving upward, right, as shown in the diagram. As electrons move upward, they collect on that lower plate of the capacitor as shown in figure 5.2. just I showed you the figure, whatever I told. Hence the lower plate accumulates a net charge or negative charge that produces an electric field in the dielectric, and this electric field forces electrons to leave the upper plate at the same rate that they accumulate on the lower plate, right. Therefore current appears to flow through the capacitor, right, and as the your what you call the charge builds up, right, voltage appears across the capacitor, right. So as the charge builds up, voltage appears across the capacitor. So we can say that the charge accumulated on one plate is stored in the capacitor, because if one plate is plus charge, another will be minus, but both the plates if you say, then it will be 0. So that's why we can say that the charge accumulated on one plate is stored in the capacitor, right. So if we go to the next, then note that the total charge on both plates is always 0, because positive charge in one plate suppose is balanced by the negative charge of equal magnitude on the other plate. So total will be 0. So when you say the total charge, it is either of the two plates. So from the above explanation we say that where a voltage source V is connected to the capacitor, the source deposit a positive charge q on one plate and a negative charge minus q on the other plate as shown in this figure. Suppose a voltage is applied between the there are two plates. So this side, this is the plus terminal of the voltage, right, source, and that way plus charge accumulated and minus q will be accumulated. Total charge will be 0, right. So, when we say capacitor's total charge, it is either of the plate, it is plus and this is minus. So, this is a simple diagram. So, the amount of charge q is directly proportional to the applied voltage V, such that q is equal to C V. This is you know also from your physics, right. So, higher secondary physics. So, here C is constant of proportionality is known as capacitance of the capacitor, right, and the unit of the capacitance is farad, right. So, this you know that q is equal to C V. So, from equation 1 we may define that capacitance is the ratio of the charge on one plate of a capacitor to the voltage difference between the two plates, right. So, in fact, capacitance it does not depend on q or V, right. So, it depends on the physical dimension of the capacitor. For the parallel plate capacitor, as shown in the figure 1, figure already I have shown. So, C is equal to epsilon into A into D, where A is the surface area of each plate, D is the dielectric distance between two plates, right, and epsilon the permittivity of the dielectric material between the plates, right. So, this is known to us, this equation you are familiar with this from your higher secondary physics. So, from figure 4, now this one shows the circuit symbol for the fixed and variable capacitor. In this case variable means just to make an arrow, so this is variable. Now, when the current I is entering into the positive terminal of the capacitor, the way you have marked it here, that means in this case the capacitor is charging, right, it is charging. If the current leaves from the positive charge, or what you call that positive terminal, if this current leaves from this positive terminal, so capacitor is discharging, right. This is the convention we will follow. So, let me clear it. So, this is the fixed capacitor symbol, and this is the way we have shown the your variable resistance R, that way we have shown same way, and this is circuit symbol fixed, this is for fixed and this is for figure B for variable capacitor, right. So, just now I told you, according to passive sign convention, current is considered to flow into the positive terminal of the capacitor when the capacitor is being charged, right, and out of the positive terminal I told you when the capacitor is discharging. Now, to obtain the current voltage relationship, the capacitor that we can take the derivative of that is your q is equal to in the equation 1, that q is equal to C V. Therefore, dq by dt is equal to C into dV by dt. That is why we are writing here, taking the derivative of this equation 1 with respect to time, right. So, dq, and we know from the very first chapter the basic concept that I is equal to dq by dt. We also know that I is equal to dq by dt, right. So, therefore, I is equal to dq by dt. So, let me clear it. So, that means I is equal to, therefore, I is equal to dq by dt left hand side, therefore, I is equal to C into dV by dt, right. So, this is equation 5. This is the current and voltage relationship for a capacitor. Assuming positive sign convention, the relationship shown in figure 5, this side is I, this side is dV by dt, the rate of change of voltage, this is I and this is the slope C, right. So, it is a linear, it is a linear equation basically, right. Therefore, C, when C is independent of I or dV or V. So, that means capacitors that satisfy equation 5 are said to be linear. From this characteristic also you can find that it is said to be linear. So, here one thing is there, many places you will find it is written book, it is not book, you please write chapter in this chapter, right, not book. Book was never completed actually, right, not completed. So, we will assume that it is a linear capacitor, right. So, because of this relationship we will say C is completely independent of I or V. So, it is a linear capacitor. So, next is the voltage current relation of the capacitor can be obtained by integrating both sides of equation 5 we will get, because here we know that I is equal to C into dV by dt, right, dV by dt, right. So, that means my dV will be 1 by C I dt. So, if you integrate both sides, right, if you integrate both sides, it will be minus infinity to t some limit you fix, right. So, question is now that let me clear it. Now, question is that this limit we have put minus infinity to t, and we are writing actually v t 0 that 1 upon C t 0 to t I dt plus v t 0. Actually, this equation if I write like this 1 upon C sometimes a minus infinity to t 0, right. If you write I dt, right. So, if you write I dt, then plus then t 0 to t then I dt, this way you can write. So, this equation is here, this is this equation, right, t 0 to t, and this equation 1 by C you are writing actually your what you call that is v t 0, your what you call that is v t 0, this equation we are writing. Actually, this let me clear it. Actually, this term that 1 by C when you write minus infinity to t 0, right, your then I dt, if you try to write this equation this way, you know that your what you call that in the past sometime that your what you call that your in that capacitor, right, that voltage may be 0. I mean that V minus infinity at some time in the past it was 0, right. There was no voltage, right, capacitor was uncharged. So, and this part, that means this part if we write like this basically if you make it like this, that 1 upon C I dt and minus infinity to t 0, right. If you make t 0 is some time, right, and from t 0 to t that this part is here. So, if you write like this and if you try to integrate, because 1 upon C I dt will be basically your say your whatever we have done, that is your dV, right. If you integrate this, it will be, if you integrate this one, it will be v t 0 minus say v minus infinity. So, and some your what you call some time in the past that maybe this v minus infinity is equal to 0, right. So, that means your what you call that your capacitor at that time you can say that there is no voltage across the capacitor v some part of the time in the past, right. So, in that case what will happen, only v t 0 will be there. That is why this let me clear it. That is why this equation is there t 0 to t and this v t 0, it actually should have been v t 0 minus v of minus infinity, but v of minus infinity should be 0, right. Or we can write from the relationship we know from this equation your what you call, we know this one that q is equal to C v or q t at time any time t 0, q t 0 is equal to C v t 0, right. This is what we have written, v t 0 is equal to q t 0 upon C, that means this term, right, is the voltage across the capacitor at time t is equal to t 0. Hope this you have understood this. Actually, whenever you take this one, that is basically we take that past history of the current flowing through the capacitor, right. That is the idea. So, anyway, let me clear it and just hold on. So, that means V t 0 is equal to Q t 0 by C is the voltage across the capacitor at time t 0. Therefore, this equation 7, that means this equation 7 shows that capacitor voltage depend on the past history of the capacitor current, right. And because of that V t 0 is here. So, hence the capacitor say we can say has memory, that is a property that is often exploited, right. So, that is why this equation we are writing that from the past we have taken at some time at present t. So, minus infinity to t 0 plus t 0 to t, that what I wrote previously, and I told you that v minus infinity will be 0. So, in that case, so the instantaneous power delivered to the capacitor is P is equal to V I, right, but I is equal to C into dV by dt. So, upon substitution, if I am not writing here, it is understandable. So, put I is equal to C into dV by dt here. So, it will be CV dV by dt. This is equation 8. Now, the energy stored same as before in the capacitor is given by minus infinity to t p dt, right. So, it is p into dt, say p is the power V I and multiplied by time. So, this is energy and minus infinity to t. So, is equal to, you can write C into minus infinity to t and your p is equal to CV dV by dt you put here, the expression of p you put here, it is CV dV by dt. C is a constant taken outside of this integration and then V into dV by dt. So, dt gone. So, it will be C integration of minus t V into dV, right. Now, if you integrate, if you this is understandable simple thing, if you integrate then it will be half C V integration will be V square by 2. So, half C V square t is equal to minus infinity to t, right. Therefore, the capacitor was uncharged at t is equal to minus infinity. I told you that at the past, in the past at some time capacitor will remain uncharged. So, V minus infinity will be 0, I told you, right. Therefore, if it, that means it will be half C, it will be half C V square minus your, it is understandable actually it is V t square, but t here is omitted, just put V square minus it will be half C V minus infinity square. Actually, it should be like this, it will be actually half C V square if you take function of t, then minus half C V square minus infinity, but V minus infinity is 0. So, t is omitted here, simply we have written half C V square. So, this is equation 10, right. So, next you take that V is equal to Q by C. We know that Q is equal to C V and substitute here, if you put it here then you will get W is equal to Q square by 2 C. This is equation 11, right. So, this is that your what you call that energy equation, right. This energy stored in the capacitor, that is your what you call half C V square or half C Q square, right. So, equation 10 and 11 give the energy stored in the electric field that exists between the plates of the capacitor. That you have capacitor, you have two plates. So, energy stored in what you call in the electric field that exists between the plates of the capacitor. Since an ideal capacitor cannot dissipate energy, right, this energy can be retrieved, like resistor, the energy is dissipated in the form of heat, but in this case, in the case of ideal capacitor, it cannot dissipate energy, the energy can be, this energy can be retrieved. So, following are the important properties of a capacitor. First one is from equation 5, that when voltage across a capacitor is not changing with time, that means your I equal to, that is equation 5, dV by dt. When voltage across a capacitor is not changing with time, that is your DC voltage. Suppose for example, I am making it for you. Suppose this is time, right, and this is voltage, and if you take a DC voltage, it is a constant. So, any time, any place, any time, any point you take the derivative is dV by dt will be 0. Therefore, if it is a DC voltage, so I will be is equal to 0. That means, when the voltage across a capacitor is not changing with time, the current through the capacitor is 0, right. This is of course a steady state condition when you apply DC voltage. When you see the DC transient after this topic, at that time we will see the behavior of capacitor as well as inductor, that will come later. So, thus a capacitor is an open circuit to DC. When you are going for steady, not at the time of switching at the time of switching things are different, right, but thus a capacitor is open circuit to DC. However, if a DC voltage is connected across a capacitor, your what you call the capacitor charges. Suppose you connect a DC voltage across a capacitor will be getting charged, right. So, let me clear it. So, second point is the voltage on the capacitor must be continuous, right. It must be continuous. The capacitor resists an abrupt change in voltage across it. I have underlined this, right. Conversely, the current through a capacitor can change instantaneously, that we will see in the DC transient time, right, not now. So, conversely, the current through a capacitor can change instantaneously. So, particularly after learning this behavior of capacitor inductor, particularly in steady state condition, but when we will consider the DC transient after covering this topic, at that time we will know much more about behavior of the capacitor as well as inductor during your what we call that transient condition, I mean switching, right. So, that is why your conversely the current through a capacitor can change instantaneously, right. So, this is one thing, and next one is an ideal capacitor cannot dissipate energy. I told you earlier, right. Capacitor takes power from the circuit when storing energy in its field, right, and returns previously stored energy when delivering power to the circuit, right. So, now this is all about capacitor. So, because we have to consider DC transient. So, that's why that and at the same time we will consider AC circuit. At that time resistance, capacitance, all this your what you call inductance all will come. So, that is later, that is your after completing DC transient we will go for single phase AC circuit. At that time we will know much more, right. And of course, we will not study AC transient as far as your as far as I can say that first year engineering syllabus is concerned, right. So, next we will take some examples, say some example. For example, that calculate the charge stored on a 3 microfarad capacitor with a 20 volt across it. Also find the energy stored in the capacitor. A very simple thing. It is given 3 microfarad, Q is equal to CV. So, C is 3 microfarad, that is 3 into 10 to the power minus 6 farad, and voltage is 20 volts. So, it is 60 microcoulomb, right. So, store energy is half CV square, half C is 3 into 10 to the power minus 6 farad, microfarad you convert it to farad. So, half into 3 into 10 to the power minus 6 into V square 20 square, that is 600 microjoules, right. Next one is, it is given that current through a 2 microfarad capacitor is IT is equal to 6 into e to the power minus 3000 t milliampere. You have to determine the voltage across it, assuming initial capacitor voltage is 0, right. So, we know this formula that V is equal to 1 upon C 0 to 2 integration of I dt plus V 0. I mean, if we go back, I mean this equation, right. I am going back. So, this equation V is equal to 1 upon C I dt, that is equation 7, right. Then again we will come down. So, in this case you assume that this is equation 7, right. So, it is 1 upon C 0 to t I dt plus V 0. We have taken the initial time t 0 is equal to 0, but V 0 is equal to 0. In the problem it is given current through a 2 microfarad capacitor is much, determine the voltage actually, assume that capacitor voltage is 0, that is initial capacitor voltage is 0, that means V 0 is equal to 0. So, here it is V 0 is equal to 0 and C is 2 microfarad. So, 1 upon C, that is 2 into 10 to the power minus 6, it is 0 to t, that 6 into e to the power minus 3000 t into 10 to the power minus 3, because this current was given in milliampere. 6 into e to the power minus 3000 t milliampere, you are converting everything to ampere. So, multiplied by 10 to the power minus 3. So, that is why here it is multi into dt. If you integrate it, V will be 1 minus e to the power minus 3000 t volt. This is the answer, right. So, this easy example, So, now next one is figure 5.6a, that is I will say 6a because it is chapter 5, shows a simple circuit and the voltage Vt is shown in figure 6b. You have to plot Qt and It. Now, question is, it is given this circuit is given, a simple series circuit, one voltage source is connected with the capacitor C in series. C is equal to given 1 microfarad and It is current flowing through it is It, right. And here it is your what you call that waveform of the voltage is given. So, actually this drawing is little bit like this, it will be actually here, right. So, it is actually, if you take the before telling you, if you take the slope of this straight line, so this is 10 volt and this is in microsecond, it is microsecond. So, if you take the slope of this straight line, it will be this is 10. So, here it is 10 and this is your what you call, this is your 2, right. So, slope will be 10 divided by, it is microsecond, 2 microsecond, that means 2 into 10 to the power minus 6 volt per second. This is the slope of this straight line, right. This is the slope, so tan theta, this is the slope. Similarly, for this one, this is the slope, say this is the slope. In this case, here for this straight line, here it will come. So, it is 1 second only, 4 to 5 means only 1 second and this is 10. So, as this is the angle is more than 90. So, this is one what you call slope will be negative. So, it will be minus 10 and 4 to 5 means this is 1 microsecond, because it is in microsecond. So, it will be 1 into 10 to the power minus 6 volt per second. This is actually slope of the straight line, and this is constant, and this is constant from 2 to 4 second, it is constant, right. So, this is the voltage, that means voltage from 0 to 2 it is a time varying, and again from 4 to 5 microsecond it is time varying. In between 2 to 4 microsecond it is constant. This voltage source is given, right. So, let me clear it. Now, we know that Q is equal to CV. So, in general we can write QT is equal to CVT, right, and C here is 1 microfarad, that means 10 to the power minus 6 farad. So, it is 10 to the power minus 6 into Vt, that means we can write Q your unit of Q is coulomb. So, it is Vt into, it is 10 to the power minus 6. So, Vt microcoulomb, right. So, there should not be any confusion. In 10 to the power minus 6 you can convert this Vt microcoulomb, right. Now, plot of Qt is shown. Look, the plot of Qt will be Qt is equal to Vt microcoulomb, right. So, Qt is actually directly coming to Vt, that means this shape of that Qt will be same as your Vt, because Qt is equal to Vt microcoulomb. So, whatever shape is there for Vt, it will be same shape, right. Only thing is that unit will change. So, if you look at the graph, that Qt, this is my Qt, y axis is Qt, and this is my t, the microsecond, but it is microcoulomb, it is 10, shape remains same, everything will remain same, right. Only thing is that unit will change, because Qt is equal to basically Vt, right. Because we have taken that C is equal to 1 microfarad. Had it been some other value, then this 10, it should not have been 10, it should be something else, right. Now, second thing is that IT also you have to plot, that how we will plot IT. So, now it is given, we know that I is equal to C dV by dt, that is known. So, in general we can write IT is equal to C dVt by dt. C is equal to 1 microfarad. So, here you put 10 to the power minus 6 converted to farad, that is why 10 to the power minus 6 into dV by dt, because C is given 1 microfarad. Now, from figure 6b, that means this is figure 6b, this is figure 6b. Now, this your what you call that the 0 to your slope we have seen that 10 upon 2 into 10 to the power minus 6, and this is passing through the origin. So, basically we know that any equation of a straight line passing through an origin y is equal to mx plus c. So, c is 0. So, basically from that you can find out actually y axis is Vt. So, and slope is 10 by 2 into the power minus 6. So, Vt will be is equal to your 2 into your 10 by 2 into the power minus 6 into t. So, if it is given here, we will come to the figure later. So, in between 0 to first find out in between 0 to your 2 second dVt by dt will, the slope is 10 by 2 into the power minus 6. That slope we computed initially I told you. So, it will be 5 into 10 to the power 6 volt per second, and in between 2 to 4 second dVt by dt 0, because it is at that time it is your what you call a pure DC quantity, right. It is not time varying, it is independent of time 2 to 4. So, its derivative will be dVt by dt is 0, right. And another thing is in between 0 to your what you call in between 4 to 5 second, I told you minus 10 by 1 into 10 to the power minus 6. So, basically minus 10 into 10 to the power 6 volt per second, right. Therefore, for this all this your what you call all this rate of change of voltage in different time interval now have been computed. Now, we know that in between 0 to 2 second, we know IT is equal to C into dVt by dt. So, C is equal to 10 to the power minus 6 and dVt by dt 5 into 10 to the power 6 is equal to 5 ampere, right, in between 0 and 0 to 2 second. Now, in between 2 to 4 IT is 0, because dVt by dt is equal to 0, this dVt by dt is equal to 0, right. And similarly, in between 4 and 5 second IT is equal to C into dVt by dt. So, dVt by dt 10 to the power minus 6 your what you call that minus 10 into the power 6 volt per second. So, in this case your C is 10 to the power minus 6, that is farad, 1 microfarad. So, 10 to the power minus 6 farad into minus 10 into 10 to the power 6. So, 10 to the power 6 and 10 to the power 6 cancel, it will be minus 10 ampere, right. So, plot of IT is shown in this figure now. Therefore, in between your 0 to 2 microsecond, it is 5 ampere, it is 5 ampere, it is a constant we have calculated. Then 2 to 4 second IT is 0, so it is 0, and then 4 to 5 second, now it is minus 10 your what you call ampere. So, that is minus 10, that 4 to 5, this is the plot for IT. I hope you have understood this one, right. So, this simple thing, very simple thing, only you have to understand step by step. Now, this is that your what you call that just for your understanding only, each and every step I have computed for you, so that we should not I mean you should not face any problem for solving. So, figure already I have shown. So, now under DC condition, now find the energy stored in the capacitor in figure 5.8. So, this is my figure 5.8. You have to find out that your what energy stored in the capacitors. So, this is 1000 ohm, 3000 ohm, 6000 ohm, and this is 20 microfarad, this is 10 microfarad. Now, we will redraw the circuit, right, under DC condition, that 10 microfarad, 20 microfarad, it will be open at steady state, right, and 20 volt DC is applied. So, if you redraw the circuit, this is open, say voltage across this 20 microfarad is V1, this voltage is V1 and this voltage is V2, right. So, this is open. So, this is open. So, this current is I, the I is flowing like this, I is flowing like this, right, because this is open, this is open, right. So, 1000, 3000 and 6000, so 10,000 ohm, right. Therefore, I is equal to your 20 by your 10,000 ampere, right. This is your what you call this thing, that means that is equal to actually 2 milliampere, right. So, this is your I, that I once you compute the I, then you can easily compute the V1 and V2. So, before showing you the calculation, so if you see the what will be V2, because same I say just 1 minute, the same current I is flowing through this, right. So, V2 will be actually V2 will be this 3000 and 6000, 3000 plus 6000 into I, that will be your V2, because this 3000 6000 are in series, right, and V1 will be 3000 into your I, because this is the voltage across V1 is the voltage across the 3000 ohm resistor. Once you get this V1 and V2, you know C1 and C2, you can calculate half CV1 square and half CV2 square, the energy stored, right. So, now you will get that your what you call that I is equal to, I told you, the 2 milliampere, V1 I told you that 3000 into the current I, 2 into 10 to the power minus 3, that is 6 volt, and V2 is equal to 9000 into I told you it is 9000 into 2 into 10 to the power minus 3, 18 volt. This is milliampere, means 2 into 10 to the power minus 3 ampere. So, this is a 2 into 10 to the power minus 2 into 10 to the power minus 3 ampere, and this is 2 into 10 to the power minus 3 ampere, 18 volt. Therefore, W1 is equal to half C1 V1 square. So, half C1 is given 20 microfarad. So, 20 into the minus 6 into V square. So, 6 into 6. So, 360 millijoules. It is in terms of millijoule, right, because 10 to the minus 6 is there. Similarly, half C2 V2 square is equal to half into your C2 value 10 microfarad. So, 10 into 10 to the minus 6 farad into voltage square 18 into 18, it will be 1620 millijoule, right. So, that means how to, that means whenever steady state DC is applied, right, capacitor will behave like an open circuit, that is why capacitors are open, and circuit solution is very easy, right. So, this is very simple thing, only you have to understand few basics. Thank you very much, we will be back again.